For the second section, our module 10.2, we're now going to get into some of the boundary layer discussion. So within boundary layers, we're going to take a look at the normalized boundary layer equations, some similarity parameters, and then the functional form of the solutions. Then we'll get into discussion on the physical interpretation of the dimensionless parameters, along with our boundary layer analogies, specifically looking at our heat and mass transfer analogy, evaporative cooling, and our Reynolds analogy. So again, within this module here, we'll go through the theory behind these topics, talk about some of our key equations, go through some practical applications, and then do out some problem solving together. So within our module 10.2, we're taking a look at boundary layers, and this relates back to our textbook, to chapter 6, sections 5 through 8. So as we jump into our module 10.2, the first topic we want to take a look at is our boundary layer similarity. So as applied to the boundary layers, the principle of similarity is based upon determining the similarity parameters that facilitate application of results obtained for a surface experiencing one set of conditions to geometrically similar surfaces experiencing different conditions. Next, we want to recall how the introduction of the similarity parameters, our Biot number and Fourier's number, permitted generalization of the results for a transient 1D conduction. Now, our dependent boundary layer variables that are of interest to us here are tau sub s, q double prime, or our h, where we can come over here and recall that our tau sub s is going to be our shear stress, our q double prime is our heat flux, and h is our heat transfer, our convection heat transfer coefficient. So those are our dependent boundary layer variables, but for a prescribed geometry, the corresponding independent variables are going to be, for our geometrical, we're going to have our size L and our location, which are x and y. For hydrodynamic, we're going to have our velocity v, and for fluid properties, we're going to have our hydrodynamic and our thermal. For hydrodynamic, we have our rho, which is our density, and mu, which is our viscosity, and for thermal, we have our C sub p, which is our specific heat, and our K value, which is our thermal conductivity. So hence what we have right here, we can take a look here for u. This is a function of x, y, L, v, rho, and our mu right there, which is our x and y is our location, as we saw up here. L is going to be our size. V is going to be our velocity. Rho is going to be our density, and mu is our viscosity. Now for our tau sub s, or our shear stress, this is going to be a function of x, again for our location right there, L being the size, V being the velocity, rho for our density, and again mu for our viscosity. So now continuing on with the similarity considerations, we can take a look down here and see our temperature here is now going to be a function of our x and y, that location right there, our L length, our V velocity, then we have our rho, our density, our mu, our viscosity right there, and we have our C sub p for specific heat, we have our K for thermal conductivity, our T sub s for our surface temperature, and our T sub infinity, our surroundings. So I've noted that over here, our location is our x, y, then we have our L for our size, our V for our velocity, our density is rho, our viscosity is going to be our mu, our specific heat is our C sub p, our thermal conductivity is our K, our surface temperature is our T sub s, and our surrounding fluid temperature is our T sub infinity. Now our H right here is going to be a function of our x, L, and V, where again our L is that size, our V is our velocity, then we have again our density, we have our viscosity, specific heat, thermal conductivity, surface temperature, and the temperature of our surrounding fluid right there. So this is our function for time, for temperature, and our function for H right here. Now our key similarity parameters can be inferred by non-dimensionalizing the moment and energy equations. So we can go back to our moment energy equations and start from there and figure out how we can non-dimensionalize them. So what we're going to do is we're going to recast our boundary layer equations by introducing dimensionless forms of the independent and dependent variables that we just discussed. Now this is going to relate back to our equations 6.31 to 6.34 in our textbook. Well, our dimensionless parameter here, variable x star, is going to be equal to our x over L. Y star is going to be equal to our y over L. U star right here for our dimensionless parameter there is equal to u over v. And our v star right there is our dimensionless parameter that's equal to v over v. And we have our temperature right here, star, for dimensionless parameter is going to be the difference between T minus T sub s, where T sub s is surface temperature, all divided by T sub infinity, which is the surrounding fluid temperature, minus T sub s, our surface temperature. So now if we neglect our viscous dissipation, the following normalized forms of our x momentum and energy equations can be obtained. So these relate back to our equations 6.35 and 6.36 in our textbook. So we have our dimensionless parameter u right here times our partial of u with respect to x, both dimensionless as we denote here. So this u star comes up to this relationship right here. Plus we have our v star right here, this dimensionless parameter from this relationship up above here from these equations 631 to 634 in our textbook, times our partial of u with respect to y, again, both dimensionless. This is equal to the negative. Now we have the derivative of our p star with respect to our x right there, so dp star over dx star right there, plus 1 over our Reynolds number, times now our second partial right there, second derivative partial right there of our u star with respect to our y right there. So this relationship, along with this relationship, can both be found in the table and relate to our equations 635 and 636. So the second equation here, again, that same u star right here, which is again our u over v right there, times our partial now of temperature in this case for here, with respect to our position x, plus now our v star related back up to here right here for our dimensionless parameter there, times the partial of t with respect to y, is equal to 1 over our Reynolds number. Now we have a Reynolds number as well, our PR value right there, times now our second partial derivative of temperature with respect to y there. Again, this all comes from that table related to these equations. So what we're seeing with these relationships here is that our dimensional variables can be written in terms of these new dimensionless variables. For example, from our equation 6.31, we have that x is equal to our x star L and that y is equal to our y star L right there, where our x star and our y star are the dimensionless variables right there. So we can put these now in terms and relate our dimensional variables and put them in terms of these new dimensionless variables. So the resulting expressions for our x, y, u, v, and t, and our CA may be substituted into equations 6.28, 6.29, and 6.30. Now, in order to obtain these dimensionless forms of the conservation equations, we can go to our table 6.1. So by normalizing our boundary layer equations, 3 very important dimensionless similarity parameters are going to evolve. And we're going to now introduce these in this table 6.1 shown below. So we can see in our table 6.1 from our textbook, this is the boundary layer equations and their y direction boundary conditions in non-dimensional form. So if we take a look at this table, what do we have here? Well, we can see over here on the left, we have our boundary layer. So we have 3 different types of boundary layers here. We have velocity, thermal, and concentration. So along with this, we have our conservation equation. So it's right here for velocity, our conservation equation is given by this relationship in 6.35. For thermal, our conservation equation is given by this relationship in 6.36. And these are the 2 equations we just looked at in the previous slide. And for concentration right here, our conservation equation is given by this relationship 6.37. Now for each of these velocity, thermal, and concentration, we can also see we have our boundary conditions over here for the wall and for free stream as well. And these are given by the relationship 6.38 through 6.40, again related to velocity, thermal, and concentration for our boundary conditions. And last over here on the far right, we have our similarity parameters right here, where for our velocity, we have our Reynolds number is equal to VL over V right there. This is 6.41. For thermal, we have our relationship 6.42. And for concentration, we have our relationship shown in our equation right here in 6.43. So this is a great table to reference back to for all of these 3 different boundary layer conditions for velocity, thermal, and concentration to get our conservation equation, our boundary condition, and our similarity parameters. So now let's continue on with our similarity considerations. I want to take a look at our Reynolds number and our Prandtl number. So for our Reynolds number, we can see we have this ratio here of our rho VL over mu, where our rho is our density, our V is our velocity, our L is the size, and our mu is our viscosity. We can reduce this down and simplify to this relationship here, and this is what's known as our Reynolds number. Now, we can do the same thing for our PR number over here, our Prandtl number right here. We can see the ratio here is our Cp times our mu over K, where Cp is a specific heat, our mu is our viscosity again, and our K is our thermal conductivity. So we can reduce this down, and what the Prandtl number is going to be defined as is the ratio of our kinematic viscosity, also referred to as our moment diffusivity, and our thermal diffusivity. Now for prescribed geometry, we have the relationship down here, our dimensionless parameter, our u star right here, is a function of our x star and y star, both dimensionless parameters right there, and our Reynolds number that we saw up above by this definition here. So now we can also see that we have our T sub s, our shear stress is given by this relationship here, which is our mu, which is again our viscosity times our partial of u with respect to y, evaluated when y is equal to 0, and this is equal to our mu value of viscosity times our v velocity all over our L, the size, times our partial of u with respect to y, both dimensionless there, evaluated on our dimensionless y is equal to 0. So now if we take a look at our dimensionless shear stress, this is also known as our local friction coefficient, or our C sub F right here. So this is given by the relationship that we have our T sub S right there, which does appear from this T sub S relationship there for our shear stress, divided by our rho V squared, or our density times our velocity squared, all divided by 2. And this is equal, we can reduce this down here to 2 over our Reynolds number, plugging this relationship up here. So we can see we can move this around between those two relationships to plug in for our Reynolds number there, times our partial of u with respect to y, both dimensionless, evaluated when our dimensionless y is equal to 0. Now for this here, we see we have this relationship right here. Well, this is going to be equal to a function of our x dimensionless x star right here and our Reynolds number right there, and our C sub F right here can reduce down to, now when we plug in this relationship here up above, to C sub F is equal to 2 over our Reynolds number times the function now here of our x star times our Reynolds number there. Now for prescribed geometry, we have the relationship here of our dimensionless parameter for temperature right here is equal to a function of our x star, y star, dimensionless location right here, Reynolds number, and our Prandtl number right there. And our h is given by this relationship here. We have our negative kf times our partial of temperature with respect to y, evaluated when y is equal to 0, all over our temperature difference right here between our surface temperature and our surrounding fluid temperature, Ts minus T infinity. So we can reduce this down a little bit, plug in for our relationships here, and we can see that this is equal to our negative kf over L times now our ratio right here between our temperature difference between our surrounding fluid temperature and our surface temperature, all over our surface temperature minus our surrounding fluid temperature right there. And this is times now our partial of our dimensionless temperature with respect to y star right there, dimensionless right there, evaluated when our y star is equal to 0. So this now then becomes this relationship here. We have our positive kf over L times our partial of temperature with respect to y, both dimensionless, evaluated when y is equal to 0. So next we'll take a look at our dimensionless local convection coefficient. So this is our NU, or our local Nusselt number right here, and this is equal to our HL over our KF, which is then equal to our partial of our dimensionless temperature with respect to y star, dimensionless position y right there, evaluated when our y star is equal to 0, which is a function here of our x star, which is our dimensionless x parameter right there, our Reynolds number, and our Prandtl number. So what I'm going to do is go to our table 6.2 in our textbook. What we have here is some selected dimensionless groups of heat and mass transfer. So we have our group, our definition, and our interpretation of it right here. So these are just a couple. There's a lot more included in this table in your textbook. But I just want to go through a couple of these for some of these you've seen before. So for example, let's take a look at our Biot number right here, our BI right there. So the definition of this, we have our HL over our K sub S. An interpretation over here, this tells us this is the ratio of our internal thermal resistance of a solid to the boundary layer thermal resistance. So this physically gives us an interpretation of what this is, what we're physically measuring. So a lot of times we're just blindly plugging into these equations. And this table here really gives us a good idea of what we're doing, and why we're doing this, and how it relates physically back to the type of problem we're doing. So we can see we have this right Biot number, our mass transfer Biot number, bond number, coefficient of our friction. We also have our Fourier number that we've looked at, and so on and so forth, all the way down to our friction factor. And again, there's a bunch more of these in our table 6.2 in our textbook. And again, this is a great idea. One, it gives us our relationship, our governing equation for all of these, and it tells us the actual physical interpretation, so we know what we're doing with these problems we're solving when we're plugging in for these relationships. So now let's take a look at our Reynolds analogy. So we have the equivalence of dimensionless momentum and energy equations for negligible pressure gradient. So this right here, when we have negligible pressure gradient, what that's saying is our dP star over our dx star right there, the derivative of our p star with respect to our x right there, both dimensionless, is approximately equal to 0, and our Prandtl number right here is equal to 1. So with that relationship there for our negligible pressure gradient, we have the following relationship. So we can see right here we have our advection term and our diffusion terms right here. So on the left-hand side of our equation, we again have this relationship. We've seen this before in a similar form, where we have our dimensionless parameter here, u, which is equal to our partial of u with respect to x, both dimensionless there, plus our v star, and we have equations for all of these that we can reference back to. We saw earlier in this module, times our partial of u with respect to y, again, both dimensionless, is equal to 1 over our Reynolds number, times our second partial derivative of our u star with respect to our y star squared right there. And we have a similar relationship down here, but now instead of our U value here, we're looking at our temperature T value, and we have this following relationship that we can see here. And again, for all these dimensionless parameters, we can reference back to our textbook and earlier in this module for those relationships equations. So for our equivalent boundary conditions, our solutions are going to be of the same form. So we have these relationships that we see here. We have now the relationship now here between our U and our T dimensionless parameters right here, which is again the difference between our top equation up here and our bottom equation down there. So for equivalent boundary conditions, we can see those two are going to be equal to each other there. So therefore, this partial right here from this relationship up above is going to be equal to this relationship here. So our partial of U with respect to Y and our partial of T with respect to Y right there, dimensionless, where our Y star is equal to 0, are both going to be equal to each other. And then we have this relationship down here that our Nusselt's number is equal to our C sub f times our Reynolds number over 2. So again, this is for equivalent boundary conditions. Now we also have our Stanton number right here, our ST, and this is defined by the following equation that we see right here. The ST is equal to our H over our rho V C sub P, which we've gone through all these variables. Again, one thing I do want to do is for a side note, is whether you write them off to the side to remember exactly what they are, what units they are, and how they physically relate to your problem, or the other option is you can always flip back to the beginning of your book and take a look at that list of symbols. That's always a great way, and there's nothing wrong with that. If you're not quite sure, wait, how am I using this? Because these variables change textbook to textbook, author to author, and course to course. So making sure you actually understand what each of the variables in that you're plugging in for, what those physically are, and what dimensions they are, that's important, especially if you're doing some unit analysis out and you want to make sure everything checks out right as you're plugging one equation into another. So this right here is equal to our Nusselt's number all over our Reynolds number times our Prandtl number right there. So that's just relating now back to our new Stanton number. So next I want to take a look at our modified Reynolds analogy. This is an empirical result that extends applicability of the Reynolds analogy that we looked at earlier. So we can see the relationship we have down here for our local friction coefficient given by this relationship shown here, where we have that C sub f over 2 is equal to our ST, where recall our ST we defined up here above is our Stanton number given by this relationship right here, times our Prandtl number right here to the 2/3 power, and this is equal to our lowercase j sub h, which is our Colburn J factor for heat transfer. And this holds true for our values here of 0.6 to 60 for our PR number. Now, this is going to be applicable for laminar flow if our differential pressure right here, our pressure differential right here, is approximately equal to 0. And it's generally applicable to turbulent flow without any restrictions on that. So now let's apply some of that theory governing equations that we just saw within this module to an example problem. So here's the example problem we're going to take a look at. What I'm going to do is go through my hand solution to this problem with you. So let's take a look at an example problem. And this problem here tells us that experimental tests using air as a working fluid are conducted on a portion of a turbine blade as shown in the sketch. So here's our sketch down here with the turbine blade. It tells us the heat flux to the blade at a particular point, x star, you see we have an x star that we're interested in here, on the surface is measured to be heat flux is equal to 95,000 watts per meter squared. So to maintain a steady state surface temperature given to us as 800 degrees Celsius, heat transferred to the blade is removed by circulating a coolant inside the blade. So we have a coolant channel down here in order to do that. Let's take a little bit closer look at our diagram here. So we can see there's our coolant channel. We have our surface temperature of 800 degrees C. We have our length here of L is equal to 40 millimeters. We have our heat flux of 95,000 watts per meter squared. We have our ambient temperature over here for air. So T sub infinity is equal to 1,150 degrees Celsius. Velocity is given to us as 160 meters per second. And these are our original conditions. So now that we've read through the problem statement, taken a look at the diagram, have a little bit of an idea of what's going on, let's figure out what they're asking us to solve for. So they're asking us to solve for two different things in this problem. The first thing they want us to do is to determine the heat flux to the blade at this position x star if the temperature is reduced now down to T sub S1 is equal to 700 degrees Celsius. And they're doing this by increasing the coolant flow. That's the first part of the problem they want us to solve for, is when we have this reduced temperature. Part two they want us to determine the heat flux at the same dimensionless location, this X star again, for a similar turbine having a blade with a chord length of L is equal to 80 millimeters. So instead of L equals 40 millimeters, they want us to change that to L is equal to 80 millimeters. When the blade operates in airflow at the same T infinity is 1150 degrees Celsius, velocity is 80 meters per second, and our surface temperature is the same, 800 degrees Celsius. So two different things it needs to solve for. So now that we've had a chance to look through the problem statement and given schematic, we want to go through and write out exactly what they have in the problem statement that we know, what we're looking for, and what assumptions we're going to make. So we have two different cases here, because remember from the problem statement they asked us to solve for two different things. So one of the main differences there was a reduced surface temperature. So in case 1, we're actually dealing with a surface temperature of 700 degrees Celsius. So for case 1, surrounding ambient temperature of the air, 1,150 degrees Celsius. Velocity V1 given to us is 160 meters per second. Our L1, our length here is 40 millimeters, which we convert to meters right away of 0.04 meters. So that's that length over here, L. And our surface temperature, T sub S1, is 700 degrees Celsius. So we've redrawn out our diagram over here, slightly simplified, just in terms of general variables now, because they'll change from case 1 to case 2. So we have our heat flux at the surface, our surface temperature, our coolant channel, our length L, velocity and temperature of our surrounding ambient air. So now that we have our diagram there and we've looked at case 1, let's go ahead down to case 2. So case 2, a couple things will change. The overall length will double and the surface temperature will go back to our 800 C. So for case 2, our ambient temperature for air is 1,150 degrees Celsius. Velocity stays at, velocity is at 80 meters per second for V2. Our length here is 80 millimeters. We convert to meters is 0.08 meters. And our surface temperature here, TS2 for case 2, so you can see my indices 2, 2, and 2 for case 2, is at 800 degrees Celsius. So now what are they asking us to solve for? Well, for both of these cases, they want us to find the heat flux at this position X star. Assumptions we're going to make, well, in the problem statement it told us it was steady state. We're going to assume incompressible flow. We're also going to assume constant air properties. Now that we've gone through our problem statement, clearly defined what we're given in the problem statement, the two different things they're asking us to solve for, case 1 and case 2, have our initial diagram and our assumptions written down, our next step is to go through our approach for our solution. And the key thing we want to do here is come up with our general governing equations. So for our case here, what we want to look at is Newton's law of cooling. So this will be our first governing equation here. So we have our heat flux is equal to H times T infinity minus Ts. We have our ambient temperature and our surface temperature here. We can rearrange this and solve for our H. We do this here, and H is equal to our heat flux divided by our temperature difference of T infinity minus T sub S, which is our air temperature and our surface temperature of our blade. So from our known conditions given in the initial diagram, we can then solve for H. So we can plug in for these values up here. So we have our heat flux given to us, we have our temperature of the air, we have our surface temperature given to us for each of the cases. So we'll do this here, we'll plug this in for this case here. H is equal to our 95,000 watts per meters squared. Temperature difference here is 1,150 minus 800 degrees Celsius. We do this out here and we end up with, one thing we want to note is our units in the end are going to have a K in it. This has a C. You can do the conversion, but the difference of the two will be the same, whether it's C or K. We can do the conversion in the end. So if you notice, my units from unit analysis here is watts per meter squared times Kelvin. So this is still correct. H is equal to 271.43 watts per meter squared times Kelvin. Now, we assumed constant properties for air, so our L and our K do not change. So now that we have our H value here, we want to take a look at case 1. So for case 1, we want to go back and solve for our Q double dash 1 or our heat flux for case 1. So we can go back to Newton's law of cooling, plug in our specific variables for this here, which is T sub S1 here. So our heat flux for case 1 is equal to our H value that we just solved for times this temperature difference here. So plug in our known values. Our heat flux for case 1 is equal to 271.43 watts per meter squared times Kelvin, right here, times our temperature difference. So our temperature difference is 1,150 again in degrees Celsius minus our 700. So this is the difference here. But now we're dealing with our surface temperature that's reduced to 700 degrees Celsius. So you can plug that value in there. And again, difference in temperature, Celsius, Kelvin, doesn't really matter. If you're worried about this, convert to Kelvin and prove it to yourself as well. So we do that out. We get our numeric value here for our heat flux for case 1 is equal to 122,000 watts per meter squared. So now that we've solved for our heat flux for case 1, we want to go ahead and do the same thing for case 2. But the first thing we want to do is realize that there's going to be a difference between case 1 and case 2. So in case 2, the main difference is we have a larger blade, so the length increases, it doubles in length. So it goes from 40 millimeters to 80 millimeters and doubles. The airflow is reduced, so the velocity decreases by a factor of 2. So now, due to this fact, the Reynolds number is going to remain the same. It does not change because our length is doubling, but our velocity is decreasing by a factor of 2, which will keep our Reynolds number the same. And to prove that for ourselves, we have here for case 1, our Reynolds number here in this for this guy is equal to velocity 1, length 1, over our viscosity here. So we plug in our values here. Our velocity for case 1 is 160 meters per second. Our length is 40 millimeters or 0.04 meters, all over our viscosity V, which will remain the same. So this gives us a value for Reynolds number for this case of 6.4 over viscosity. Now, for case 2 here, we have V2, L2 over viscosity here, where V2 is now 80 meters per second, and our length doubles to 80 millimeters, or 0.08 meters. So 80 times 0.08 is the same as 160 times 0.04, which gives us 6.4. So our Reynolds number does remain the same for case 1 and case 2 due to the fact that our velocity is going to be changed by 2, a factor of 2, and our length is changing by a factor of 2 inversely. So it keeps these exactly the same for the Reynolds number. Now what will change is the convection coefficient. So in order to prove that this will change, what we want to do is take a look at equation 6.49 on page 401 of our textbook for our Nusselt number. So we have this general equation here. The Nu is equal to our H, our convection coefficient, times L over our K value there. And this is going to be a function of our position X star, our Reynolds number, and our PR number. And we can see we can define each of those by their equations, and none of these will change. But if we look down here for the Nusselt number for case 1 versus the Nusselt number for case 2, those are both going to be the same. But what's going to change in here is our L value changes from L1 for case 1 to L2. We know that that's given in the problem statement. But our K's are going to stay the same for this guy here. So if these guys stay the same and these change, that means our H's must change. So H2 cannot be equal to H or H1 in this case here. So now we're going to continue on with that equation there. So we can look for case 1 versus case 2. And what we want to do is rearrange this in order to solve for our H2. So this is what we want to look for in this problem here. So we can rearrange this solving for H2, and when we do that, H2 is equal to H times L over our L2 here, where we have numeric values for all of these. So H2 is equal to our H value here, which is 271.43 watts per meter squared times Kelvin. We solved for in the first part of the problem. And then we have our ratio of our lengths. So our length for case 1 divided by our length for case 2, where this is half of that. So this is 0.04 meters divided by 0.08 meters. We do this through, and it's basically dividing our H value for case 1 by 2. So 271.43 divided by 2 in the same units of watts per meter squared times Kelvin. We do this out and we get an H2 value here of 135.71 watts per meter squared times Kelvin. Now recall what they asked us to solve for on the problem statement is for our heat flux. So we still need to solve for our heat flux for case 2, where we now have our H value for case 2. So we can go back into our equation here that we've seen before for our H2 is equal to our heat flux divided by our temperature difference. We can rearrange this again and solve back again for our heat flux for case 2. So Q is equal to our H2 value here times our temperature difference. We have numeric values for all three of those. So we can say that our heat flux is now this H2 value that we just solved for of 135.71 watts per meter squared times Kelvin, times our temperature difference in Kelvin here, which is now going to be 1150 minus 800 for case 2. We do this out, and what we end up with is our Kelvins cancel, so we're actually a heat flux in the correct units of 47,500 watts per meters squared. So now we've solved this for case 1 and for case 2 for our heat flux. So I want to take a look at one more example problem and go through my hand solutions for this example problem 6.28 as well. For our next problem, let's take a look at 6.28 from our textbook. So in this problem here, experiments have shown that for airflow at a temperature of T infinity is equal to 35 degrees Celsius, at a velocity v1 equal to 100 meters per second, the rate of heat transfer from a turbine blade of characteristic length L1 equal to 0.15, now they actually give it to us in meters for this problem here, and surrounding surface temperature of T sub S1 is equal to 300 degrees Celsius is given to us as a value of Q1 of 1500 watts. So they want us to find what would be the heat transfer rate from a second turbine blade with a different characteristic length of 0.3 meters as compared to 0.15 meters, operating at a surface temperature of 400 degrees Celsius now as compared to 300 degrees Celsius, and a surrounding temperature is still the same of 35 degrees Celsius, but with a different velocity now of 50 meters per second rather than 100 meters per second. So the surface area of the blade may be assumed to be directly proportional to its characteristic length. So now that we've read through the problem statement for 6.28, what we can do next is write out all the variables, values, units, and how they apply to our problem. So that's what we've done here in our given section. So we know we have air temperature T sub infinity is equal to 35 degrees Celsius, and I've gone ahead and converted this to Kelvin right here, 308.15 Kelvin. We have V1, our velocity, is equal to 100 meters per second. We have length 1 in meters of 0.15 meters, and we have our surface temperature TS1 equal to 300 degrees Celsius. And again, converted to Kelvin, it's 573.15 Kelvin. And we have our Q1 value given in the problem statement is 1500 watts. Now I've separated it out and done it for 2. Case 2 here, we have L2 is equal to 0.3 meters. Our surface temperature of the second turbine blade, TS2, is 400 degrees Celsius, or converted to Kelvin, 673.15 K. Our second velocity, V2, is 50 meters per second, so half of that of V1. And our surface area density is proportional to the characteristic length here. Now down below, what I've drawn here is drawn out our two different cases, a diagram for each. So we have our air, T infinity, V1. Case 1 here, here's our area, A1. Here's our surface temperature, TS1. Here's Q1 there, and our length, L1. Now over to the right, I've tried to proportionately draw out our case 2 here. Well, now L2, which again, if we go up top, L2 is 0.3, which is double that of L1, which is 0.15 meters. And we still have our air, T infinity, and our velocity, V2 here. Our area is now A2, and we now have this Q2 that we're going to solve for, and our surface temperature, T sub S2. So this is great that I have one page here where I clearly define case 1 and case 2, both of my schematics, all my variables, the actual numerical numeric values and the units that we're using for these. So this is a great page to reference back to as we're going through our solution. So now that we've had a chance to go through and write out all of our variable names and figure out what they're asking us to solve for in the problem for case 1 and for case 2, we next want to go and create all of our assumptions. So the first assumption we're going to make is that we're dealing with steady state conditions. We're also going to assume constant properties, and we're also going to have the assumption that the surface area A sub s is directly proportional to the characteristic length L. We're going to assume negligible radiation, so we're not dealing with any radiation terms here. We're also going to assume that the blade shapes are geometrically similar, even though their lengths and their sizes are different. So after we have our assumptions, the next step is to figure out our governing equation for the solution to this problem. So the governing equation we're going to start with here is the average Nusselt number. Now this comes from chapter 6 on page 401. We can see our general equation here. Our average Nusselt number is equal to our h bar times L over K, which is a function of the Reynolds number and our PR number. So from this here, what we realize, if this is a function of Reynolds number, we're going to need to calculate the Reynolds number. So in order to calculate the Reynolds number, we're going to want to do it for both blades. So I'm going to stop here and switch over to a general equation for Reynolds number. So here's our governing equation that we're going to use to calculate our Reynolds number. So we have that RE is equal to, in this case we can do the right hand side of the equation here, U is the velocity of the fluid with respect to the object in meters per second, L is the characteristic length in meters, and we have V on the bottom is our kinematic viscosity of the fluid in meters squared per second. So this is what we're going to use to calculate Reynolds number 1 and Reynolds number 2 for the two different shapes and sizes of the turbine blades. So now we take that equation for our Reynolds number and we apply it to both cases, because again we need to calculate the Reynolds number for both of the blades. So for blade 1, case 1, what we have here is Reynolds number 1, REL1, is equal to V1L1 over V1. Well, this is velocity, this is length, and this is viscosity. So now we know our velocity 1 for case 1 for blade 1 is 100 meters per second. Our length 1 is 0.15 meters, and our viscosity 1 we're just going to leave as V1 here. So this ends up being, for Reynolds number for 1 for blade 1, 15 meters per second over our viscosity 1. So we're going to do the same thing for case 2 for the larger blade 2, V2L2 over V2, where this is second velocity, length, and viscosity here. So our second velocity is 50 meters per second. Our length is 0.3 meters, which is double that of 1. And we're going to leave this as V2 for our viscosity for blade 2 here. So we can do this here, and we can see that this is equal to this, and we know those must be equal. So from the relationship, we can determine that V1 is equal to V2. So therefore, Reynolds 1 and Reynolds 2 are equal to each other, and PR1 and PR2 are all equal to each other based upon this. So now that we've shown that the Reynolds numbers and the PR numbers are equal and constant, from case 1 to case 2, or blade 1 to blade 2, the next thing we want to do is go back to the Nusselt number here. So we go back to our key equation here, and now we can say that Nusselt number 1, average Nusselt number 1 is equal to average Nusselt number 2. So this is equal to, for case 1 for our blade 1, H1 average times L1 over K1, and for the second case, the larger blade, H2, L2, and K2. So we can set these equal to each other based upon this here. So we have H1, L1 over K1 is equal to H2, L2 over K2, where our K1 and K2 do not change between the two different cases, the two different blade sizes, so those remain constant. So now we can go back through and solve. So when we do this here, we can see the K's cancel out there, so we're left with H2 is equal to H1 times the ratio of L1 over L2. So now we recall, for our heat transfer equation here, Q is equal to our area times H times our temperature difference here. So for our specific case here, Q1 is equal to that area times H1 times T sub S1, minus T infinity there. And then what we can do is rearrange this equation here so that H1, if we solve this for H1, is equal to Q1 divided by the area times that temperature difference between TS1, or surface temperature in case 1, minus our ambient temperature for the AR T infinity there. Now with this relationship for H1, we can go back up in here to this relationship here in this equation and plug in terms of H1. So now we'll have our Q1A, TS1, and T infinity instead of our H1 there. So once we plug that relationship back up into the equation above, we end up with what we see here for a relationship here in the box, that our average H2 is equal to the ratio of our lengths, L1 over L2, times our Q1 divided by A1 times the temperature difference of our surface temperature, TS1, minus our surrounding ambient air temperature, T infinity. Now this here, we can then plug in, and we can use this relationship to calculate our Q2 value. So we plug this in down to this equation for Q2 here, which again we recall was Q2 is equal to our H bar 2 times A2 area times our temperature difference of the surface temperature 2 minus our ambient surrounding temperature T infinity of the air. Plug in this relationship here, and we have what we see here now of Q2 is equal to that ratio L1 over L2, so all this is coming from above here, of Q1 divided by A1 times TS1, our surface temperature, minus the temperature T infinity of our surroundings here. Now this is times the right hand side of this equation here, which is A2 times the surface temperature TS2 minus T infinity. We can rearrange and simplify this here. We can see we have our A2 over our A1, pull that out in front, and we have now our L1 over L2 ratio of our lengths times the ratio of our areas, A2 over A1, times our Q1 times our temperature difference for case 2 divided by our temperature difference for case 1, where this is our surface temperature minus our ambient temperature, surface temperature minus ambient temperature here for case 1. Then, with this equation here, we can plug in our known values. And this is why it's great that we have that first page of our solution, so we can reference back to that and plug in all those known values from one location directly into this here. We start to plug in, we know our L1 and L2, we can plug those in, and we start to plug in our A2 and A1 here, and then we realize we have this assumption that we have a proportionality between A1 and L1 and A2 and L2, so if we were to do that, these would end up canceling out. Now, if you're not convinced of that from the assumption, I'd say go ahead and calculate your areas, plug it in, and prove this to yourself here, but I'm going to go ahead with our assumption and assume that, so now we're just left with the right-hand side of the equation, which is our Q1 times our temperature difference when we plug in here of our TS2 is 400 degrees Celsius. Our T infinity is 35 degrees Celsius for both cases. And our TS1, our surface temperature for case 1, is 300 degrees Celsius. So now I can plug in for my Q1 value, which was given as 1500 watts when I plug in here. So Q2 is equal to 1500 watts times, when we do this guy out here, this is 365 degrees Celsius, 265 degrees Celsius. Plug those in, run this to our calculator. Q2 equals 2066 watts.